Tonight, we are going to look at one of the most ambitious and genuinely unsettling ideas humanity has ever seriously considered. Not a metaphor, not a thought experiment, an actual engineering proposal. A ship so large it would function as a city. A voyage so long that the people who leave Earth would never arrive. Their grandchildren might not arrive. Their great-great-grandchildren. People who will have been born between the stars, who will have never seen a sky. Those people are the ones who land. This is a generation ship. And once you understand what it actually means, it changes the way you think about distance, time, and what it means to be human. This is a story of what happens when human beings decide they want to go anyway, not in a metaphorical sense, not in a science fiction sense, but in the most literal engineering, biological, sociological sense possible. What would it actually take to send people, living, breathing, eating, loving, arguing, grieving people, to another star? The answer, it turns out, is one of the most extraordinary ideas our species has ever seriously considered. And it begins, as so many extraordinary ideas do, with a problem of scale so vast it feels almost insulting. The distance that breaks intuition. Our nearest stellar neighbor is a small, dim red star called Proxima Centauri. It sits at a distance of approximately 4.24 light-years from Earth. That number, 4.24 light-years, sounds modest when you first hear it. After all, we talk casually about distances of millions of kilometers in our own solar system, and 4.24 feels almost intimate by comparison. But a light year is a distance that light travels in 1 year, and light moves at roughly 300,000 kilometers per second. In a single second, a photon of light travels a distance roughly equivalent to circling the Earth 7.5 times. In 1 year, that same photon covers approximately 9.46 trillion kilometers. Multiply that by 4.24. Proxima Centauri is about 40 trillion kilometers away. To put that in terms that might mean something, the Voyager 1 spacecraft, launched in 1977, is the most distant human-made object ever built. As of the mid-2020s, it has been traveling for nearly 50 years. It is moving at roughly 17 kilometers per second, faster than almost anything humanity has ever constructed. And at that speed, it would take Voyager 1 approximately 73,000 years to reach Proxima Centauri. If it were aimed in that direction, which it isn't, 73,000 years. To put that in human terms, 73,000 years ago, our species had not yet left Africa in significant numbers. We had not invented writing or agriculture or cities or mathematics or music notation or any of the 10,000 things we consider the architecture of civilization. The gap between that moment and now, the entire sweep of recorded and unrecorded human history, is roughly the time it would take our fastest spacecraft to reach the nearest star. This is the first thing you have to understand about interstellar travel. It does not merely require better technology. It requires a fundamentally different relationship with time itself. Proxima Centauri and its world. Before we talk about how to get there, it is worth spending a moment on where we might be going. Because in 2016, astronomers made an announcement that genuinely changed the conversation. A planet was confirmed orbiting Proxima Centauri. It was designated Proxima Centauri b, and what made it remarkable, what made scientists across the world sit up a little straighter, was its location. Proxima b orbits within its star's habitable zone. That is a range of distances from a star where liquid water could, in principle, exist on a planet's surface. Not where it does exist, not where life does exist, but where the temperatures might, under the right conditions, allow it. The planet has a minimum mass of approximately 1.3 times that of Earth, which places in a category we call a rocky terrestrial planet, rather than a gas giant. It completes one orbit around Proxima Centauri every 11.2 Earth days, which sounds extraordinarily fast, but Proxima Centauri is a much smaller, cooler, dimmer star than our Sun, which means its habitable zone sits much closer in. The planet is not baking in heat. In terms of the energy it receives, it gets roughly 65% of the solar energy that Earth receives from the Sun. On paper, some of those numbers sound promising. In practice, the situation is considerably more complicated. Proxima Centauri is what astronomers classify as an M-dwarf star, also called a red dwarf. These are the most common type of star in our galaxy, quiet, long-lived, and in many respects stable. But Proxima Centauri is also what is called a flare star. It periodically releases intense bursts of radiation, including powerful X-ray and ultraviolet flares that are far more energetic relative to the star's baseline output than anything our sun typically produces. Current estimates suggest that Proxima b currently receives approximately 30 times more extreme ultraviolet radiation than Earth does, and around 250 times more X-ray radiation. What that means for a planet trying to hold on to an atmosphere, and for any life trying to exist on its surface, is genuinely uncertain. It depends on a cascade of factors: whether the planet has a strong magnetic field, whether it retains enough volatiles like water and nitrogen during its formation, whether the atmosphere is thick enough to absorb and scatter high-energy radiation before it reaches the surface. Scientists have modeled several possible states for Proxima b. Some of those models produce a world with a dense carbon dioxide atmosphere, warm and perhaps bearing liquid water. Others produce a desiccated, airless rock, stripped of its oceans by billions of years of stellar activity. A 2024 study led by researchers at the Hebrew University of Jerusalem examined the role of ozone in stabilizing Proxima b's atmospheric temperature distribution, finding that ozone has a measurable influence on wind patterns and hemispheric temperature balance. Though the researchers were careful to note this points toward the complexity of the system rather than confirming habitability. The honest summary is this: we do not know whether Proxima Centauri b is habitable. We do not know whether it has liquid water, a breathable atmosphere, or even a stable climate. It orbits within the habitable zone, and that is a meaningful fact. But it is a starting point for investigation, not a conclusion. What makes it the default destination for most serious discussions of interstellar travel is not certainty about what is there. It is simply that it is the closest. At 4.24 light-years, it is as near as any star gets. And for the purposes of the engineering challenge we are about to explore, that proximity, even at 40 trillion kilometers, is a genuine advantage. There are other candidate worlds. GJ 1061d orbits a red dwarf about 11.9 light-years away. Teegarden star C is roughly 12.5 light-years distant. Neither is as close as Proxima b, and in a journey that will take centuries regardless of destination, even a few extra light-years matter enormously. So we point at Proxima. We do our best to imagine what might be there. And then we ask the harder question: how we go, the wall that physics builds. The instinctive answer, when people first think about traveling to another star, is to build a faster rocket. We went from horse-drawn carriages to spacecraft in about 150 years. Surely, given enough time and enough engineering, we can build something fast enough. The problem is not engineering ingenuity. The problem is physics, and physics does not negotiate. Any rocket, any vehicle that carries its own propellant and burns it to generate thrust, is constrained by something called the Tsiolkovsky rocket equation, derived in 1903 by the Russian mathematician Konstantin Tsiolkovsky. The equation describes the relationship between a rocket's final velocity, the exhaust velocity of its propellant, and the ratio of its initial mass, fuel included, to its final mass, the empty vehicle. The mathematics are unforgiving. To reach even 1% of the speed of light using chemical propulsion, the kind we use in conventional rockets, you would need a fuel-to-payload mass ratio so enormous that it is not merely impractical, it is physically absurd. The entire observable universe does not contain enough chemical propellant to accelerate a meaningful spaceship to interstellar speeds using chemical rockets. This is why no serious proposal for interstellar travel involves chemical propulsion. The physics simply will not allow it. But what about other forms of propulsion? This is where the conversation becomes genuinely interesting, because over the last several decades, physicists and engineers have produced a range of serious, peer-reviewed proposals for interstellar travel. None of them are simple. All of them face profound technical challenges. But they are not fantasies. They are real ideas, grounded in real physics, waiting for technologies that may or may not arrive within a human lifetime. The menu of serious options. The first class of proposals involves using something other than chemical fuel to drive a spacecraft. The most studied of these is nuclear pulse propulsion, the idea of detonating a series of nuclear devices behind a massive pusher plate to drive a spacecraft forward. A detailed engineering study called Project Daedalus, conducted by the British Interplanetary Society in the 1970s, concluded that a fusion-powered spacecraft could theoretically reach Barnard's star, about 5.9 light-years away, in roughly 50 years, traveling at approximately 12% of the speed of light. The fuel of choice in that design was helium-3, a rare isotope of helium that is believed to be relatively abundant on the Moon and in the outer solar system, but which is currently available on Earth only in trace quantities. The engineering of such a vessel would be staggering. Project Daedalus envisioned a two-stage vehicle with a total mass of roughly 54,000 metric tons, the vast majority of which was fuel. The payload, only about 450 metric tons, and it would arrive at its destination in flyby mode with no means of slowing down. A more recent study, Project Icarus, revisited and refined Daedalus over the course of several years in the 2010s, exploring variations on design and the fuel choices. The conclusions were broadly similar. Fusion propulsion is theoretically capable of achieving interstellar speeds, but the engineering requirements are immense and control fusion itself. The ability to sustain a fusion reaction and extract net energy from it remains an unsolved problem as of the mid-2020s. The second class of proposals involves not carrying the fuel at all, but instead harvesting it from the interstellar medium. A physicist named Robert Bussard proposed in 1960 what became known as the Bussard ramjet, a spacecraft equipped with a vast electromagnetic scoop, hundreds or perhaps thousands of kilometers in diameter, that would collect the diffuse hydrogen drifting between the stars and use it as fuel for a fusion engine. In principle, such a vehicle would have no fuel limit. It would feed on the galaxy itself. In practice, subsequent analysis found serious problems. The density of hydrogen in interstellar space is far lower than Bussard had hoped, roughly 1 atom per cubic centimeter on average. More damaging, theoretical work in the 1970s and later suggested that the drag from scooping up interstellar hydrogen might actually slow a Bussard ramjet faster than the fusion engine could accelerate it. The concept is not universally dismissed, but it currently has no mainstream engineering pathway. The third class of proposals involves using energy transmitted from a remote source rather than carried on the vehicle. The most discussed modern version of this idea is laser sail propulsion, which forms a conceptual core of the Breakthrough Starshot Initiative, announced in 2016 with funding from tech investor Yuri Milner. The concept involves an array of ground-based lasers generating a combined beam of extraordinary power, on the order of 100 gigawatts, directed at a sail of thin reflective film, perhaps a few meters across, carrying a tiny payload of gram-scale electronics. The laser would accelerate the sail to approximately 20% of the speed of light in a matter of minutes. Breakthrough Starshot's stated ambition was to send such probes toward Alpha Centauri, the three-star system that includes Proxima Centauri, and have them arrive within roughly 20 years of launch. They would take photographs, measure the stellar environment, and transmit data back to Earth before continuing their journey outward into the dark. The technical challenges are immense. Building a laser array of the required power does not currently exist. Keeping the beam focused on a tiny sail across vast distances involves pointing precision that far exceeds anything built so far. The sail itself would need to survive traversing the interstellar medium at a significant fraction of the speed of light, where even a tiny dust particle becomes a violent collision. And the payload, gram scale, means no person, no large instrument suite, no attempt to break an orbit. Breakthrough Starshot, as of the mid-2020s, remains in an early research and development phase. No sail has been launched. No laser array has been built. The concept is scientifically credible, but it is an early-stage vision rather than an imminent program. The fourth option, antimatter propulsion, is in many ways the most powerful theoretical concept. Matter-antimatter annihilation releases energy with an efficiency that dwarfs every other reaction known to physics, converting mass directly into energy at 100% efficiency in principle, compared to roughly 0.7% for fusion and a fraction of a percent for fission. An antimatter rocket could theoretically accelerate to a substantial fraction of the speed of light, and then decelerate at the destination, allowing it to stop and enter orbit rather than flying through a high speed. The problem is production. Antimatter is produced in particle accelerators in quantities measured in nanograms per year. The energy required to produce it vastly exceeds the energy you would recover from annihilating it. There is no known natural reservoir of antimatter accessible to us. As a propulsion concept for interstellar travel, antimatter remains fascinating, but dependent on physics and manufacturing breakthroughs that have no current roadmap. The shape of the problem. After reviewing all of these proposals, a pattern emerges, and it is an important pattern because it reframes the entire question. Every concept that could plausibly accelerate a large spacecraft to interstellar velocities, nuclear pulse, fusion ramjet laser sails, involves either technology that does not exist, resources that are not accessible, or payloads so small that no human being can be on board. The gap between what physics permits and what engineering can currently achieve is not small. It is enormous. And here is where the generation ship enters the conversation, not as a compromise or a fallback, but as a genuinely different philosophy of the problem. Because every propulsion concept we just discussed shared an assumption so deeply embedded that we barely noticed it. The assumption is this: the journey should be fast enough that the people who leave Earth are the people who arrive at the destination. That is the natural human intuition about travel. You get in the vehicle, you go, you arrive. But what if you let go of that assumption? What if, instead of trying to make the journey short enough for one human lifetime, you build a vessel designed to sustain human life for 10 lifetimes? Or 20? What if the ship itself became the world, and the destination was something the passengers' great-great-grandchildren would experience? Not them. This is a generation ship. And once you allow yourself to think in those terms, the engineering problem does not become simpler. In some ways, it becomes harder, but it becomes a different kind of problem. It shifts from a question of propulsion physics to a question of biology, sociology, ecology, psychology, and ultimately philosophy. It becomes less a question of how fast you can go, and more a question of how well you can live. The idea that wouldn't go away. The concept of a ship carrying multiple generations of human beings between the stars is older than most people realize. In 1918, at a time when the first liquid-fueled rockets were still years from being built, an American engineer and rocket pioneer named Robert H. Goddard wrote a private document he called The Ultimate Migration. In it, he described a scenario in which the death of the sun, billions of years in the future, might force humanity to flee to another star system. His proposed vehicle was a vast enclosed ark, carrying passengers who would sleep in some form of suspended animation or otherwise sustain themselves across the immensity of deep time. The document was not published until after Goddard's death. He appears to have considered it too speculative, perhaps even too strange, to share with his professional colleagues. But the instinct it represents, the recognition that crossing between stars might require entire lives, entire generations, was prescient. In 1929, the British philosopher and biologist J.D. Bernal wrote a visionary essay describing what he called space cities, enormous self-contained habitats drifting through the cosmos, housing communities of thousands. Bernal was not specifically focused on interstellar travel, but his vision of human communities living and thriving in constructed environments in space laid conceptual groundwork that later thinkers would explicitly carry into the interstellar context. The idea received its most detailed early engineering treatment in 1964, when a physician and engineer named Robert Ensman proposed what has since been called the Ensman Starship. Ensman envisioned a vessel driven by pulsed thermonuclear explosions, with a massive sphere of frozen deuterium, a hydrogen isotope, at its bow serving as both fuel store and radiation shield. The living quarters would be housed in rotating cylinders aft of the fuel sphere, providing artificial gravity through centrifugal force. Ensman's design was meant to carry an initial crew of 200 people on a journey lasting several centuries, with the population expected to grow over time as the ship traveled. Ensman was working decades before modern computational tools, before genetic sequencing, before the discovery of confirmed exoplanets. His specific numbers may not survive modern scrutiny, but his approach, treating the generation ship as an engineering problem to be solved in serious detail, not merely a narrative device, was genuinely ahead of its time. These were isolated efforts, visions scattered across decades, produced by individuals working outside mainstream scientific institutions. For most of the 20th century, the generation ship remained a concept discussed more often in science fiction than in engineering literature. Writers like Robert Heinlein and Isaac Asimov explored its dramatic and philosophical possibilities long before institutions took it seriously. That began to change in the 2000s and accelerated significantly in the 2010s and 2020s, as the confirmed existence of thousands of exoplanets transformed interstellar travel from pure speculation into a question with actual destinations. If you know there are worlds around nearby stars, the question of visiting them becomes less abstract. It becomes pressing, not immediately practical, but the kind of problem that serious people feel entitled to take seriously. The return of the serious. In 2012, a nonprofit organization called Icarus Interstellar launched a project specifically dedicated to conceptual engineering of generation ships. They call it Project Hyperion. Over the following years, it produced a series of peer-reviewed papers examining the population genetics, the life support requirements, the social structures, and the propulsion options for multi-generational interstellar voyages. The results were published in academic venues, presented at conferences including workshops organized by the European Space Agency, and quietly moved the generation ship from the province of speculation into the province of scholarship. Then, in November 2024, a successor to that effort, organized under the Initiative for Interstellar Studies, a UK-based nonprofit, launched a public design competition under the same name, Project Hyperion. The competition invited interdisciplinary teams of architects, engineers, anthropologists, and urban planners to submit conceptual designs for a generation ship capable of a 250-year voyage to Proxima Centauri b. The prize pool was $10,000, modest, but the point was not the money. The point was to demonstrate that the problem could be engaged seriously by real professionals, using real knowledge from real fields. Hundreds of teams submitted entries. On July 23, 2025, the winners were announced. The first place design was called Chrysalis. It was developed by an Italian team, and what was striking about it was its scale. Chrysalis was envisioned as a cylindrical spacecraft roughly 58 kilometers in length. That is about 36 miles, designed to house approximately 2,400 people. It was not a cramped lifeboat. It was a world. The design incorporated spaces for food production, engineering and maintenance, living quarters, schools, libraries, parks, and communal gathering areas. The aesthetic philosophy was that the people aboard should not feel imprisoned. They should feel as much as possible at home. Other entries explored different geometries. Some were shaped like spinning wheels, creating artificial gravity through rotation. Others resembled stacked tori, rings of habitat layered along a central axis. One design drew its inspiration from the structure of a jellyfish, using a form of biomimicry to distribute risk across multiple modular systems. The diversity of approaches was itself revealing. There is no single agreed blueprint for a generation ship. There are principles, constraints, and trade-offs, and within those, enormous room for different visions. What the competition demonstrated, more than anything, was that the generation ship is not an idea from the past. It is an idea whose time, if not quite here, is approaching. The questions it poses, engineering, biological, philosophical, are real questions being worked on by real people in real time. What we've established. By the time you reach the end of this first part of our story, a few things should be clear. The nearest star is so far away that our fastest spacecraft would take tens of thousands of years to reach it. The physics of conventional propulsion will not solve that problem. Every serious alternative, nuclear pulse, fusion, laser cells, antimatter, faces challenges that are either unsolved or, in some cases, may be fundamentally unsolvable within constraints of what we can build. The generation ship is not the easiest option. It is the most honest one. It does not pretend that we can solve the distance problem by going faster. It acknowledges that the distance is, by human timescales, essentially infinite. And then it asks a different question. Not, how do we make the journey shorter? But, how do we make a world in which the journey itself is livable? For the people who begin it, for the people born in the middle of it, and for the people who, after 2 centuries or 3 centuries or more, look out the forward observation windows and see a new sun growing slowly brighter against the black. That is what Part 2 will explore. The engineering, the biology, the numbers, the attempts already underway to design the thing itself. But before we get there, in the quiet of this moment, in whatever still place you found to listen to this, it is worth sitting with the image for a moment. A ship moving through the dark, carrying a city's worth of human beings, all of them born between the stars, none of them having ever seen the planet their ancestors left behind, living their whole lives in a vessel under artificial light, eating food grown in hydroponic bays, raising children who will raise children who will raise children, until one day, not them, but someone descended from them, will press their face against a window and see, for the first time, a world they were always meant to reach. It is one of the most ambitious things our species has ever imagined, and unlike so many of our grand ambitions, it does not require us to break the laws of physics. It only requires us to be patient enough and wise enough to try. There is a question that serious engineers ask when they begin working on a problem of this scale. Not, can we do this? That question tends to paralyze more than it clarifies. The better question is, what would it actually take? It is a quieter question, more patient. It does not demand a triumphant answer. It simply asks you to sit down, open the notebook, and begin listing the requirements, one by one, without flinching from the ones that seem impossible. That is what this part of our story is about. The notebook, the list, the remarkable, sobering, occasionally awe-inspiring reality of what a generation ship would actually need to be. Because when you stop treating it as a metaphor and start treating it as an engineering problem, several things become immediately clear. First, it is harder than almost anyone intuitively imagines. Second, it is not obviously impossible. And third, the challenges are not only mechanical. The hardest problems, it turns out, are not in the physics. They are in the biology. And some of the hardest problems in the biology are not really biology problems at all. They are problems about what it means to be a human being. The inheritance of an idea, before we get to the engineering itself. It is worth understanding how we got to where we are, because the generation ship did not arrive fully formed. It was built, concept by concept, across more than a century of gradual thinking. We left off in Part 1 with Robert Goddard's private 1918 document and the Ensman Starship concept of 1964. But the tradition of serious thinking about long-duration human habitats in space has a parallel history that intersects with the generation ship at several important points. In 1975, NASA sponsored a summer study at Stanford University to examine the feasibility of large space habitats, not interstellar ships, but self-contained human communities in orbit around the sun or at gravitationally stable points in space. The result of that study was one of the most detailed engineering analyses ever conducted of a large closed-loop human habitat. It produced a design now known as the Stanford Torus. The Stanford Torus is a donut-shaped rotating habitat, roughly 1.8 kilometers in diameter, designed to house approximately 10,000 people in a ring that spins to simulate gravity. The interior of the ring will be pressurized and illuminated by sunlight redirected through a system of mirrors. Agriculture, manufacturing, and residential areas would all be housed within the structure. The 1975 study addressed, in considerable detail, questions of air recycling, food production, water reclamation, waste management, and structural engineering. The Stanford Torus was never built. It was a study, not a program, but its importance to the generation ship story is direct. It demonstrated that the life support engineering of a large, self-contained human community in space is not magic. It is an engineering problem, a difficult one, with many unsolved subproblems, but one that can be broken into components and addressed systematically. Later proposals explicitly incorporated the Stanford Torus as a module within generation ship designs. The World Ship Study produced by Project Hyperion in the 2010s examined a design consisting of 4 stacked Stanford Torus habitats, connected to a propulsion and power system loosely derived from Project Daedalus. The scale was enormous. A minimum population for such a vessel was estimated at 100,000 people, the threshold the researchers used to define a true world ship as distinct from a smaller crude transport. That number, 100,000, is important, and we will return to it. But first, the ship itself, the physics of the vessel. A generation ship, at its most fundamental level, is a closed system moving through open space. Everything the people aboard need to survive must either be carried from the start or produced continuously within the vessel. Nothing significant can be resupplied from outside, and the ship must function without catastrophic failure for a period measured not in years or decades but in centuries. Begin with size. There is a minimum scale below which a closed human ecosystem simply cannot function. You need enough physical volume to grow food, recycle water, process waste, maintain atmospheric composition, and house enough people to sustain a viable population and a functioning society. Various engineering studies have arrived at different minimum estimates, but the general conclusion is consistent. A generation ship cannot be small. The chrysalis design from the 2025 Project Hyperion competition, which was selected as the winner from hundreds of serious submissions, envisioned a cylinder roughly 58 kilometers long. That is not a spaceship in conventional sense. That is a small city that happens to be moving through interstellar space. Mass is closely linked to size, and mass creates the central engineering tension of any space vehicle. Every kilogram you want to move requires propellant to accelerate it, and propellant has its own mass, which requires more propellant to move, in a cycle that rapidly becomes self-defeating. For an interstellar generation ship, this tension is acute. The ship must be large enough to sustain life. But the larger it is, the more energy is required to move it, and the more difficult the propulsion problem becomes. There is no clean resolution to this tension. Different designs make different choices, accepting different trade-offs. Some prioritize a larger, more comfortable habitat, and accept a lower cruise velocity and a longer journey time. Others minimize mass aggressively, accepting more constrained living conditions in exchange for higher speed. The chrysalis design chose to prioritize the long-term psychological and social health of its inhabitants, which is a genuine and defensible engineering choice. Because a crew that deteriorates psychologically over 2 centuries is a mission failure regardless of how fast the ship is traveling. Then there is gravity. Human beings evolved in a gravitational field, and our physiology depends on it in ways that are not fully optional. In the absence of gravity, the human body changes. Bone density decreases, muscle mass atrophies, cardiovascular function alters, fluid redistribution causes intracranial pressure changes that can affect vision. These effects have been studied extensively aboard the International Space Station and by cosmonauts who have spent extended periods on the Russian Mir space station. For missions lasting months, these effects are manageable with exercise and careful medical monitoring. For a journey lasting centuries, they are not manageable in that way. You cannot simply require all 2,400 inhabitants of a generation ship to spend several hours a day on a treadmill across 10 generations. Something more fundamental is needed. The standard engineering solution is rotation. A cylinder or a torus rotating around its central axis experiences a centrifugal effect on its interior surface that mimics gravity. The perceived gravitational strength depends on the rotation rate and the radius of the structure, A larger radius allows the same effective gravity at a slower rotation rate, which is important because rapid rotation creates a Coriolis effect, a subtle difference in apparent gravity between your head and your feet that causes nausea and disorientation in human beings. For a comfortable simulation of Earth gravity, a rotating habitat needs a radius of at least several hundred meters, and ideally more than a kilometer. The Chrysalis design and most other Sirius generation ship proposals incorporate rotation as their primary gravity solution. The engineering implications are significant. A rotating structure cannot be a simple static shell. It must be built to tolerate continuous stress across centuries without fatigue failure. Bearings and rotational joints must function reliably for longer than most engineering structures in human history have existed. Radiation presents a different challenge. In open interstellar space, far from Earth's magnetic field, a spacecraft and its inhabitants are exposed to two main sources of ionizing radiation: the galactic cosmic ray background, high-energy particles originating from events throughout the galaxy, and the solar wind from Proxima Centauri, should the ship enter that star system. Both forms of radiation are biologically damaging. Over years and decades, cumulative exposure significantly increases cancer risk and can cause other physiological harm. The most practical radiation shielding for a large vessel is mass. Water, in particular, is an effective radiation shield due to its hydrogen content, and water is something the ship needs to carry in large quantities in any case. Some designs propose building a water jacket around the crew habitats, using the ship's water supply as a passive radiation shield. Other proposals use polyethylene or other hydrogen-rich materials for the same purpose. Whatever the specific material, the principle is the same. Put enough mass between the crew and space, and the radiation dose becomes manageable. None of these solutions are simple. Each kilogram of shielding is a kilogram that must be accelerated to interstellar velocity. Every engineering decision involves trade-offs that compound across centuries. This is the nature of the problem. The closed loop, keeping people alive across centuries. The most underappreciated engineering challenge of generation ship is not propulsion, it is the life support system. Specifically, what engineers call the closed-loop life support system: the network of biological and mechanical processes that continuously converts human waste products back into the air, water, and food that human beings need to survive. On Earth, this system is planetary in scale. The atmosphere, the oceans, the soil biome, the water cycle, the food web. These form a life support system of extraordinary redundancy and resilience, accumulated over billions of years of evolution and geological history. A generation ship cannot carry a planet. It must simulate the essential functions of one within a finite, human-constructed enclosure. At the most basic level, human beings consume oxygen and produce carbon dioxide. They consume clean water and produce wastewater. They consume food and produce solid and liquid waste. In a sealed environment, without continuous recycling, the oxygen runs out, the water becomes undrinkable, and the food runs out in a matter of weeks. The recycling must be nearly perfect, not 90% efficient, not 99%. The losses that accumulate over centuries from even small inefficiencies can be catastrophic. Water recycling on the International Space Station currently operates at approximately 90 to 93% efficiency, recovering most moisture from urine, sweat, and exhale breath and purifying it into drinkable water. That remaining 7 to 10% must be made up from resupply missions. A generation ship cannot receive resupply missions. It needs to do better, much better. Atmospheric management requires maintaining the right balance of oxygen, nitrogen, carbon dioxide, and trace gases, while removing toxic compounds that accumulate from outgassing of materials, human metabolism, and biological processes. On the space station, this is managed by a combination of electrolysis, splitting water into oxygen and hydrogen, chemical scrubbers for carbon dioxide, and other systems. For a generation ship, these processes must be augmented by biological approaches. Plants and other photosynthetic organisms that naturally consume carbon dioxide and produce oxygen integrating life support with food production in a unified biological loop. This is where the Biosphere 2 experiment becomes directly relevant to our story, and where the story becomes considerably more humbling. Biosphere 2 was a project constructed in the Arizona desert in the late 1980s and early 1990s. It was an enormous sealed structure, roughly 1.27 hectares of enclosed space, designed to function as a completely self-contained ecosystem. It housed 7 distinct biomes: a rainforest, an ocean with a coral reef, a mangrove wetland, a savanna grassland, a fog desert, an agricultural zone, and a human habitat. In September 1991, 8 people entered the structure and sealed the doors behind them. They were meant to live entirely within it for 2 years, growing their own food, recycling their own water, and breathing air sustained entirely by the plants within the enclosure. The experiment was scientifically invaluable. It also failed in several important ways. Carbon dioxide levels fluctuated dramatically and unpredictably, rising to levels that caused cognitive impairment in some of the inhabitants. Oxygen levels dropped significantly, partially due to carbon dioxide absorption by exposed concrete within the structure, and had to be supplemented from outside after about 16 months, which formally ended the full closure of the system. Most of the vertebrate species and all of the pollinating insects died out. Morning glory plants and cockroaches thrive in ways that disrupted the intended ecological balance. Food production was lower than planned, and the inhabitants lost significant body weight over the 2 years. The lessons were not that closed-loop life support is impossible. They were that it is profoundly more complex than it appears. Small perturbations in biological systems cascade into large effects. Carbon sequestration in unexpected materials like concrete can silently deplete the atmospheric balance. Ecological communities do not always stabilize in the ways you intend, and the gap between a functioning model and a functioning reality can be enormous. A generation ship would need to do what Biosphere 2 attempted, except not for 2 years, but for 2 centuries or more. Not with 8 people, but with thousands, and not with the option of opening the door and supplementing the oxygen supply. The closed loop must actually close. Fully, indefinitely. This remains one of the genuinely unsolved engineering problems on the generation ship's list. It is not unsolvable in principle, but it has not been solved in practice. And until it has been demonstrated to function reliably for decades at scale, any generation ship design that depends on it, which is every design, carries this uncertainty at its heart. The population question. Set the engineering aside for a moment. Assume the ship is built. The closed loop works. The gravity is comfortable. The radiation is contained. The ship is moving. How many people do you need on board? This is not a social preference question. It is, in the first instance, a genetics question, and the genetics answer is both clearer and more demanding than most people expect. Human genetic health depends on diversity. When a population is small and isolated, and its members reproduce primarily with each other across many generations, 2 dangerous genetic phenomena become increasingly severe. The first is called inbreeding depression. The gradual accumulation of harmful recessive genes expressed more frequently as close relatives are more likely to share the same genetic variants. The second is genetic drift, the random loss of genetic variants simply because, in a small population, some lineages die out by chance, independent of whether those variants are beneficial, neutral, or harmful. Over many generations, a small isolated population loses genetic diversity that cannot be recovered. The consequences are not abstract. Human populations that have experienced severe bottlenecks, whether due to disease, isolation, or historical persecution, show measurably elevated rates of certain genetic diseases. The Amish community, largely descended from a small founding population of German immigrants in the 18th century, has higher rates of specific rare genetic conditions than the general population. The Ashkenazi Jewish population, which also experienced historical bottlenecks, shows elevated rates of certain inheritable diseases, including Tay-Sachs and cystic fibrosis. These are not the results of moral failings or poor choices. They are the mathematical consequences of small founding populations reproducing in relative isolation over many generations. For a generation ship, the founding population creates exactly this kind of bottleneck, deliberately by design. The question is how large that founding population must be to prevent the accumulated genetic harm from becoming catastrophic before the voyage ends. Researchers have given meaningfully different answers to this question, and it is important to understand that the disagreement is genuine and the differences are significant. Anthropologist John Moore, in a study published in the early 2000s, estimated that a population of approximately 160 people could sustain a healthy voyage over several generations, provided that reproduction was socially managed to avoid close relative pairings. This relatively small number was based on modeling family structures and reproduction patterns, and assumed active social control over who had children with whom, a form of arranged population management that carries its own serious ethical and social problems. A substantially different conclusion came from population geneticist Cameron Smith of Portland State University, whose work in the 2010s modeled the genetics of multigenerational voyages with considerably more attention to random genetic events, disease outbreaks, and the probability of catastrophic population loss during a long journey. Smith concluded that a minimum population of around 10,000 was necessary to maintain genetic health, and that a population of 40,000 would provide a meaningfully safer margin. His modeling showed that a founding population of 500 loses roughly half its genetic diversity over 30 generations. A population of 150 loses about 80%. These are not minor discrepancies. The difference between 160 and 40,000 is more than 2 orders of magnitude, a factor of 250. A ship designed around Moore's estimate would look nothing like a ship designed around Smith's. The former might be a vessel for a few hundred people. The latter would need to be something closer to a small city or multiple ships traveling in convoy. What explains the gap? Partly different assumptions about how strictly reproduction would be managed, partly different levels of conservatism about unforeseen population losses, disease, accident, social collapse, and partly genuine scientific uncertainty about the right parameters to use in the model. Neither estimate is accepted as definitive. Both are taken seriously by researchers. The honest answer is that the minimum viable population for a multi-generational interstellar voyage is not yet known with confidence, and the range of credible estimates spans an enormous space. There is a technological wild card that could change the calculation significantly: germline cryopreservation. If a generation ship carried a large frozen bank of human genetic material, sperm, eggs, or embryos, representing hundreds of thousands of genetic donors, the effective genetic diversity aboard the ship would be far larger than the living population. Frozen genetic material could be introduced into the living population at intervals, genetically refreshing the gene pool without requiring additional living passengers. Some researchers argue that this approach, combined with a smaller living population, could preserve genetic health adequately. The technical feasibility of preserving biological material in this way across centuries of space travel, exposed to radiation, temperature fluctuations, and the passage of time, is not fully established. Long-term cryopreservation of genetic material has been achieved for decades in specialized laboratory conditions on Earth. Whether those conditions can be maintained aboard a spacecraft for 200-plus years is a question that has not been answered experimentally. Feeding 2,000 people for 200 years. Let us return to the practical and consider food. A crew of 2,400 people. The chrysalis design's target population. Each requires roughly 2,000 to 2,500 kilocalories per day, along with proteins, fats, vitamins, minerals, and sufficient dietary variety to maintain both physical health and psychological well-being across generations. Growing all of that food within a sealed spacecraft presents challenges that are different in kind from simply carrying enough calories. Carried food has a finite shelf life. Even the most stable preserved foods degrade over decades, and certainly over centuries. The only viable approach to feeding a multi-generational crew is continuous food production aboard the ship itself. The primary model is hydroponic or aeroponic agriculture. growing crops in nutrient-enriched water or mist without soil under artificial lighting. These systems have well-understood advantages for space applications. They use significantly less water than conventional soil agriculture, can be designed to fit into vertical growing arrangements that maximize yield per square meter, and can be managed without the complex microbial ecosystem of natural soil. NASA and other space agencies have studied space-based food production extensively. Research aboard the International Space Station has successfully grown leafy vegetables, including lettuce, kale, and Chinese cabbage using systems called Veggie and the Advanced Plant Habitat. These are small-scale experiments, but they demonstrate the basic feasibility of growing food in microgravity under artificial light. Scaling that to feed 2,400 people continuously across centuries is an enormous step. Estimates of the agricultural area required to fully support a crew of this size through closed-loop plant-based food production range widely depending on the caloric density of crops grown and the efficiency of the growing system. But figures in a range of several square kilometers of growing area have appeared in engineering discussions. An area that is significant but not implausible for a vessel of the dimensions envisioned by Chrysalis. The crop selection matters. Different staple crops have different caloric densities, different nutritional profiles, different water requirements, and different growth cycle lengths. Potatoes and sweet potatoes are calorie-dense and grow relatively quickly. Soybeans provide protein and fat. Wheat and rice provide carbohydrates. A balanced diet requires a thoughtful combination of crops, managed as a system rather than any single monoculture. Animal protein is a more complex question. Some proposals include small animals, insects in particular, given their high protein yield per kilogram of feed and their relatively small space requirements. The idea of an insect-based protein supplement is not appetizing to everyone, but it reflects a legitimate engineering logic. Insects convert food to body mass at rates far more efficient than cattle or pigs. They require less space, and they can be fed on organic waste from the rest of the agricultural system, completing a nutritional loop. The psychological dimension of food cannot be dismissed. Human beings do not merely eat for calories. Food is cultural, social, celebratory, comforting. A diet of optimized nutrient paste, however complete from a biochemical standpoint, would be a form of impoverishment that degrades the quality of life aboard the ship in ways that are likely to manifest as psychological harm. Generation ship designers who take the social sciences seriously consider crop variety, cooking facilities, and communal meal times to be life support infrastructure in the same sense that water recycling is life support infrastructure. Power across the centuries. Every system we have described, the rotation drive for gravity, the atmospheric processors, the water recyclers, the agricultural lighting, the heating, the computing systems that manage all of the above, requires energy. And unlike everything else on the ship, energy cannot be recycled. It must be continuously generated. In the inner solar system, solar panels are a practical energy source. At interstellar distances, sunlight fades to near nothingness. A generation ship traveling between stars cannot rely on solar power. It needs a power source it carries with it. The baseline technology for a generation ship power plant, in the judgment of most researchers, is nuclear fission. Fission reactors have powered submarines continuously for decades. The technology is mature, well understood, and capable of generating significant power from a relatively small mass of fuel. Uranium and thorium, the most common fission fuels, are dense in energy content. A relatively small quantity can sustain significant power generation for years. The engineering challenge for a generation ship is duration. A nuclear reactor that must operate without major maintenance for 200 years is a different proposition from a submarine reactor designed for 30 years with regular scheduled overhauls. The materials of reactor cores degrade under sustained neutron bombardment. Fuel must be carefully managed over the long term. Control systems must be designed with extraordinary redundancy, and the expertise to maintain a nuclear reactor must be preserved and transmitted across generations of crew members who may not have the same training as the engineers who built it. Nuclear fusion, the same reaction that powers stars, would be a more attractive power source if it were available. Fusion reactions produce less radioactive waste than fission, generate more energy per unit of fuel mass, and could use fuels like deuterium that are relatively abundant. But as noted in Part 1, controlled fusion has been an active research goal for decades and had not yet been achieved at net energy production scale as of the mid-2020s. Whether it will be available as a mature technology by the time humanity is ready to build a generation ship is genuinely unknown. It is not wishful thinking to include it in speculative designs, but it is also not something that can be assumed. Some designs propose a combination: fission for reliable baseline power generation, with fusion included as a speculative upgrade that could be incorporated if the technology matures before the ship launches. This is a reasonable engineering philosophy, designed for what you know works, and build in capacity to improve if better options become available. The chrysalis in detail. Let us spend a moment with the winning design from the 2025 Project Hyperion competition, because it represents the most recent and most rigorously evaluated public attempt to answer the question: what does a generation ship actually look like? The chrysalis design, developed by an Italian interdisciplinary team, envisioned a cylindrical vessel approximately 58 kilometers in length, roughly 36 miles. Its population was designed around 2,400 inhabitants, though the structure was planned to accommodate growth over the voyage duration. The cylindrical form rotates to provide artificial gravity on its inner surface. What distinguished Chrysalis from earlier conceptual designs was the degree to which social science informed the physical architecture. The design was not organized purely around engineering efficiency. It was organized around human life. The interior was zoned into distinct functional areas: agricultural zones, industrial and engineering spaces, residential neighborhoods, and what the designers called civic spaces, parks, open-air equivalents under artificial sky lighting, schools, libraries, medical facilities, and communal gathering areas. The philosophical premise underlying the design was explicit. A generation ship is not a vehicle that carries passengers. It is a society that moves. The people aboard do not merely need to survive the journey. They need to live meaningful, full human lives within it. They need places to gather and places to be alone. They need children to have childhoods that are genuinely childlike, not merely biologically human, but ecologically impoverished. They need art and ritual and ceremony and grief and celebration. This premise is not sentimentality. It is engineering. A population that is psychologically healthy, socially cohesive, and meaningfully engaged with its community is more likely to maintain the discipline and competence required to operate complex systems across centuries. A population that is miserable, fragmented, or purposeless is a threat to mission success, as concrete as a reactor failure. The designers of Chrysalis were drawing on a body of research in environmental psychology, the sociology of isolated communities, and a lived experience of people who have spent extended periods in extreme isolation, including Antarctic Research Station personnel, submarine crews, and long-duration spaceflight participants. All of that research converges on a consistent finding. Human beings in confined, isolated environments need more than biological sustenance to remain functional and cooperative. They need beauty and agency and connection and purpose. This was the animating idea behind Chrysalis, that the architecture of the ship should be the architecture of a good life, insofar as that can be built into physical space. The parks were not a luxury. The libraries were not a luxury. They were part of what the designers called the mission-critical human environment. Whether Chrysalis will ever be built is a question no one can answer. It is a concept, not a program. But it represents something genuinely new in the history of interstellar thinking. A design developed by people who understood that the hardest part of the generation ship problem is not the propulsion or the food or the air or the water. It is the human beings, the energy of getting there. We have discussed how to keep people alive aboard the ship. We have not yet discussed how the ship moves. The propulsion system for a generation ship operates under a different logic than the propulsion systems we described in Part 1. A generation ship does not need to travel fast. It needs to travel fast enough. The distinction matters. Breakthrough Starshot aims for 20% of the speed of light. because its gram-scale probes have no passengers to sustain, no food to grow, no ecology to maintain. Every second of travel time is irrelevant because no one is waiting. For a generation ship, the opposite logic applies. If the ship is a functioning society and the people within are living full lives, then travel time, while not irrelevant, is a less acute constraint. A journey of 150 years and a journey of 400 years are both longer than any individual human life. The difference between them matters for mission planning, but it is not the difference between possible and impossible. This means that a generation ship can use lower performance propulsion than an unmanned flyby probe. It does not need to reach 20% of the speed of light. A fraction of that, 1% perhaps or 5%, is sufficient for a journey of 2 to 4 centuries to Proxima Centauri. At 5% of the speed of light, the journey would take approximately 85 years. At 1%, it would take roughly 420 years. Both are multi-generational. Both are potentially viable. The most plausible propulsion candidates at these velocity ranges include nuclear pulse propulsion and, eventually, nuclear fusion. Nuclear pulse, using a sequence of nuclear explosions to drive a pusher plate, was the basis of both Project Orion in the 1960s and a more detailed Project Daedalus study of the 1970s. The physics is well understood. The engineering is difficult. The political and environmental questions around detonating nuclear devices in space, particularly near Earth during the launch phase, are formidable. But Project Orion demonstrated through subscale experiments that the basic concept functions. At 1% of the speed of light, a nuclear pulse system is within the range of fission rather than fusion, which means it depends on technology that exists today, at least in principle. At higher velocities, fusion becomes necessary. The chrysalis designed propulsion architecture was not specified in detail in the publicly available competition materials, but the team positioned it as fusion-based for the cruise phase. Deceleration is a challenge equal to acceleration. A ship traveling at even 1% of the speed of light carries enormous kinetic energy. Slowing down at the destination requires either a braking propulsion system, which means carrying additional fuel for deceleration, or some form of external braking, such as a magnetic sail that interacts with the stellar wind of Proxima Centauri to gradually shed velocity as the ship approaches. The magnetic sail concept, sometimes called a mag sail, was proposed by physicists Robert Zubrin and Dana Andrews in the early 1990s. A large superconducting loop of wire creates a magnetic field that deflects the charged particles of the stellar wind, creating a drag force that slows the ship. The concept is theoretically sound, though its practical performance at interstellar approach velocities is subject to ongoing research. It has the advantage of requiring no additional propellant for deceleration. No single propulsion solution for a generation ship has achieved the status of engineering consensus. What the research community agrees on is the range of what is physically plausible and the general scale of the engineering challenge. What we know, what we don't. By this point in our exploration, the shape of the problem should be clearer, not simpler, but clearer. A generation ship requires a structure large enough to support a closed-loop ecology and a viable human population, rotating to provide gravity, shielded to limit radiation exposure, and built to structural tolerances that survive centuries without catastrophic failure. A life support system that recycles air, water, and nutrients with near-perfect efficiency, integrating biological and mechanical systems in a closed loop that has never been demonstrated at scale for anything close to the required duration. A population large enough to maintain genetic health across the voyage, with a number that depends on assumptions researchers genuinely disagree about, ranging from a few hundred to tens of thousands. A food production system capable of feeding that population continuously across generations, using closed-loop agriculture under artificial light, with crop diversity adequate to sustain both nutrition and psychological well-being. A power system, most plausibly nuclear fission, potentially nuclear fusion, capable of sustained operation across centuries with maintenance performed entirely by the crew. A propulsion system capable of reaching interstellar velocities, most likely some form of nuclear pulse or fusion drive, and a complementary deceleration system capable of slowing the ship to orbital velocity at the destination. And all of this embedded in a physical and social architecture thoughtfully designed to sustain genuine human flourishing, not mere biological survival, across the span of multiple human lifetimes. None of these requirements are individually impossible. Several of them depend on technologies that exist today in preliminary form. Several others depend on technologies that are theoretically sound but not yet engineered. The combination of all of them working together reliably for centuries, that is the challenge. The generation ship, honestly assessed, is not a project for this decade or the next. It is a horizon, a point toward which serious work can be directed, even from a great distance. And yet the work is being done, slowly at the margins of mainstream space science. But seriously, the chrysalis design exists. The population genetics papers exist. The closed-loop life support research exists. The propulsion physics exists. Piece by piece, the notebook is being filled. The shape of a world. There is something that the engineering documents do not fully capture, and it is worth naming before we close this part of the story. The generation ship is not, in the end, a spacecraft. It is a civilization. A small one, bounded by curved walls and artificial light, carrying its culture and its science and its grief and its music at a tiny fraction of the speed of light through the dark between the stars. The people aboard will grow up knowing nothing else. They will fall in love and argue and discover and mourn and celebrate entirely within its enclosed space. They will look at the agricultural bays the way we look at fields. They will navigate the residential corridors the way we navigate streets. The hum of the recycling systems will be, to them, the sound of home. The schedule of artificial sunrise and sunset will structure their days the same way the actual sun structures ours. And somewhere deep in the culture that will evolve aboard that ship, in its stories, its songs, its dreams, its children's games, there will be an idea. The idea of a destination, of a world that exists at the end of all this. A sun that is not artificial. A sky that is not painted on the ceiling of a cylinder. Ground that has never been trodden by human feet. How that idea will be held and transmitted and transformed across 10 generations of people who have never seen it is one of the most interesting questions that the generation ship poses. It is not an engineering question. It is a question about memory and faith, and what human beings do with the stories they tell about why they are here and where they are going. That question, and others like it, is what Part 3 will explore. The ethics of deciding who goes. The philosophy of consent for people not yet born. The slow transformation of a human community across centuries of isolation. And the question that waits at the end of it all. What does arrival mean for people who have never known any other world? There is a moment in the design of a generation ship when the engineering diagrams run out, when the stress tolerances have been calculated, the crop yields estimated, the reactor outputs confirmed, and the population genetics modeled to the limits of the available data, when every system that can be specified has been specified, and then you are left with the questions that specifications cannot answer. Who gets on the ship? Who decide that? What right does anyone have to choose on behalf of people not yet born, the only world those people will ever know? After centuries of travel, will the community that arrives still recognize itself as human in the way the founders understood that word? And what does any of it mean, the mission, the sacrifice, the hope, if the world at the other end of the journey turns out to be barren rock? These are not engineering problems. They are the oldest problems our species has. Questions about justice and freedom and identity and what it means to belong somewhere. Questions that philosophers have argued over for millennia without resolution. The generation ship does not solve them. It concentrates them. It puts them in a sealed container, points them at a distant star, and asks them to work themselves out over the course of 200 years. This is the part of the story that no technical document addresses. And it may be the most important part. Who gets to go and who decides? Begin with the most immediate question. If humanity were to build a generation ship capable of carrying, say, 2,000 people to Proxima Centauri, and the launch window were fixed and the ship were ready, who would be on it? The first answer that suggests itself is merit. Send the best people, the most intelligent, the most skilled, the most physically healthy, the most psychologically resilient. Select for the competencies a mission requires. Engineers, biologists, physicians, farmers, educators, pilots, programmers. Build a crew optimized for success. The logic is obvious. The problems are equally obvious. Who evaluates merit? By what criteria? Any selection process reflects the values, biases, and assumptions of the people designing it. History offers abundant evidence that institutions tasked with determining who is valuable have systematically excluded people along the lines of race, gender, class, disability, and cultural background, not because those exclusions were logically required, but because the people doing selecting brought their own unexamined assumptions to the process. A generation ship that departs Earth carrying a population selected by a panel of 21st century experts will carry, embedded in that selection, every bias and blind spot those experts possessed. That population will then carry those assumptions, institutionalized, into the deep future. There is also a deeper problem. The skills most valuable for the first year of the journey are not the same as the skills most valuable for the 150th year. You cannot fully anticipate the challenges a crew will face over multiple generations. The person who saves a mission from a catastrophic social breakdown in year 80 might have been someone who scored unremarkably on any standard competency assessment at departure. Bioethicist Conrad Sosik, who has published extensively on the ethics of space settlement in journals, including Space Policy and Futures, has argued that the selection process for a generation ship is among the most morally serious decisions in the entire enterprise. His work, including a 2019 paper examining ethical frameworks for human habitation beyond Earth, emphasizes that selection criteria inevitably embody value judgments about what kind of human beings matter, and that those judgments deserve explicit scrutiny rather than being smuggled into apparently neutral technical criteria. An alternative approach is lottery, random selection from a large pool of willing volunteers who meet some baseline of physical health and psychological stability. A lottery is not meritocratic, but it has a property that merit selection lacks. It is immune to the systematic biases of evaluators. The person who wins a lottery was not chosen because someone in power judged them valuable. They were chosen by chance, which is a different kind of fairness. It is not perfect fairness, but it is a kind of fairness that does not require us to trust a judgment of selectors we cannot fully verify. A third approach combines elements of both. Define the essential competencies a ship requires. You need a minimum number of surgeons, a minimum number of nuclear engineers, a minimum number of agricultural specialists, and fill those slots through careful professional evaluation, while filling the remaining seats through lottery. This preserves the mission's functional requirements without pretending that a comprehensive meritocratic ranking of human beings is either possible or morally neutral. None of these approaches is settled policy. None has been formally adopted by any space agency or interstellar study group. They remain live ethical debates, because the generation ship itself remains hypothetical. But the debate is worth having now, while the decisions are theoretical, because the value systems embedded in selection will shape the kind of community the ship becomes. A ship whose passengers were selected by one set of criteria will develop differently over generations than a ship whose passengers were selected by different criteria. The ethics of the beginning reach forward into the entire voyage. There's a further dimension that receives less attention. The people who do not go. If a generation ship represents a meaningful chance of ensuring human survival in some form, a backup civilization against catastrophe, then the question of who boards it is also a question of who is excluded from that chance. A world that builds a generation ship and sends it to the stars has made a choice, implicitly, about which people's descendants might inherit another world, and which people's descendants will remain bound to the fate of the one they were born on. The distributive justice of that choice, who benefits and who bears the cost, who is chosen and who is not, is a question that belongs as much to political philosophy as to mission planning. The consent of the unborn, the selection problem, difficult as it is, applies to the people who make a choice, The volunteers who put their names forward, who are evaluated or drawn by lottery, who board the ship as adults with some understanding of what they are committing to. They have, in some meaningful sense, chosen this. Their children have not, and their children's children have not. And the 22nd generation of people born aboard the ship, who will be the ones who arrive at Proxima Centauri, if everything goes according to plan, have not. They did not choose to be born on the ship. They did not consent to spend their lives within its walls. They had no voice in the decision that defined the only world they would ever know. This is what philosophers call the non-identity problem, and it is one of the most vexing puzzles in moral philosophy. It was articulated with particular rigor by the British philosopher Derek Parfit in his 1984 book Reasons and Persons, a work widely regarded as one of the most important works of moral philosophy of the 20th century. Parfit's problem runs roughly as follows. Consider a person, call her Maria, born 20 years into the voyage, who has spent her whole life aboard the ship. Maria might have a difficult life by the standards we would apply from outside, confined, isolated from the variety of Earth, denied the choice of where to live or what world to call home. We might be tempted to say that it was wrong to bring Maria into existence under these conditions, that the people who decided to build and launch the ship wronged the future generations who would be born on it. But Parfit's insight was that this argument is harder to make than it appears. Maria's existence is not separable from conditions of her birth. If the ship had not been launched, or if her parent ancestors had not been on it, Maria would not exist at all. The specific combination of circumstances that produced her, including the conditions of the ship, is inseparable from her identity. She cannot coherently say that she has been harmed by being brought into existence under these conditions, because the alternative is not a better life somewhere else. The alternative is no life at all. The harm comparison that we would normally make, you would have been better off if X, does not apply in the same way. This is a non-identity problem. It seems that we cannot wrong future people by bringing them into existence in conditions that seem, from the outside, unfortunate or constrained, because those future people's very identity depends on exactly those conditions. And yet many of us feel strongly that there is something morally problematic about deliberately creating human beings who are destined to spend their lives in confinement, without choice, with a world defined for them before they were born. Parfit acknowledged this tension, and did not claim to have resolved it. He spent considerable effort in Reasons and Persons working to the possible ways of articulating what, if anything, is wrong with choices that affect the identity of future people. No fully satisfying resolution has emerged in the philosophical literature since. The non-identity problem remains genuinely open, not because philosophers have not tried, but because it touches something real and hard about the relationship between existence and well-being. How does this apply to the generation ship? Several philosophers who have written specifically about interstellar ethics have grappled with this question. One influential response, offered by thinkers including Sosik and others working in the philosophy of space exploration, is that the relevant moral obligation is not to refrain from bringing people into existence in constrained conditions, but to ensure that the conditions are as good as they can reasonably be made. If the people of the generation ship live genuinely good lives, full, meaningful, connected, purposeful, then the ethical concern is diminished, not because the non-identity problem is resolved, but because the premise that they are being harmed is weakened. This reframes the ethical obligation. It places enormous weight on the quality of life aboard the ship. It says, you cannot ask for consent from the unborn, but you can take the most serious possible obligation to build the best possible world for them. The Chrysalis design's emphasis on parks, libraries, civic spaces, and psychological well-being is not merely sentimentality. From this perspective, it is an ethical response to the non-identity problem. It is a designer saying, we cannot give these people a choice, but we can build a world worth living in. There is a further philosophical question, whether the people born on the ship should be informed, honestly and fully, of their situation, that they are on a multi-generational voyage, that they did not choose this, that the mission that defines their world was decided by people now long dead. Most contemporary ethicists who have written on this question argue that concealment would be deeply wrong. The people aboard the ship are moral agents. They deserve to understand their situation, to form their own views about it, to protest, to resist, even to decide, if they ever gain the technical capability, to turn back. Consent cannot be obtained from those not yet born, but autonomy and honest information can and must be given to those who are alive. Drift and identity. What remains after 10 generations? Suppose the ship has been traveling for 100 years. The founders, the people who stepped aboard and watched Earth recede until it was a point of light, and then nothing, are all dead. Their children are dead. Their grandchildren are old. The people alive now have no living memory of Earth. They know it from recordings, from libraries, from stories told by people who heard them from people who heard them from people who were there. What are they? This question about cultural and psychological identity across generations of isolation is not hypothetical in a way that some of the engineering problems are. We have historical examples, not of interstellar voyages, obviously, but of isolated human communities that evolved over generations in ways their founders could not have predicted or controlled. The most extensively studied are island populations. The Pitcairn Islanders, descended from the mutineers of HMS Bounty who settled on Pitcairn Island in 1790 along with Tahitian companions, developed a distinct dialect, social structures, and cultural identity that diverged significantly from their English and Polynesian origins within a few generations. The island's population was at one point as small as a few dozen people, far smaller than any serious generation ship population estimate. And the social dynamics that emerged from that extreme isolation included both cohesion and, eventually, severe internal conflict. Other examples abound. Isolated religious communities, remote agricultural villages that remained largely cut off from broader currents of cultural change for centuries, monastic communities that maintained specific traditions across long spans of time through deliberate, highly structured transmission practices. From these examples, researchers who have written about the social dynamics of generation ships, including sociologist Daniel Zwick and cultural anthropologist Cameron Smith, the latter, also notable for his genetics work discussed in Part 2, have drawn several consistent conclusions. First, cultural drift in isolated populations is not merely possible. It is, over sufficient time, essentially inevitable. The cultural practices, beliefs, values, and identity of an isolated community will diverge in their origins at a rate that depends on how much exposure they have to external influences, how actively they work to preserve their founding culture, and how many internal disruptions they experience. Second, the rate and direction of that drift are largely uncontrollable. You can attempt to preserve culture through deliberate transmission, through education, through ritual, through recorded media, through formal institutions. Every long-surviving culture in human history has used exactly these tools. But transmission is always imperfect, and every generation interprets what it receives through the lens of its own experience. After 10 generations, the language spoken aboard the ship may have drifted significantly from English as spoken on Earth. The stories they tell about Earth, the cultural memory that gives a mission its meaning, may have transformed into something with mythological qualities quite different from historical narrative. Whether this is a problem depends entirely on your perspective. From the standpoint of mission success in the strict sense, do the people who arrive at Proxima Centauri have the technical knowledge and social organization to attempt settlement? It matters less what language they speak or what stories they tell than whether they can operate the ship systems, maintain the ecology, and cooperate effectively. From the standpoint of human cultural continuity, do the descendants of Earth still carry something meaningful of the civilization that sent them? The question is both more complex and more contested. Some generation ship ethicists argue that the goal of cultural preservation is itself a form of the paternalism problem. The founders had their culture. The people born 10 generations later will develop their own, imposing the founders' values and culture on those future people. Keeping them as cultural custodians of a world they have never seen is a form of control that may not be legitimate. They may and should have the right to become whoever they become. The destination matters. Perhaps Their cultural identity along the way is their own to make. There is also the question of governance. A community of thousands, living in close confinement for centuries, would develop political structures. What those structures look like, and whether they remain just and functional, is a question that cannot be fully designed in advance. Human political history demonstrates that power concentrates, that institutions decay, that abuses emerge especially in isolated communities where external oversight is impossible. The ship's founders can write constitutional documents, design checks and balances, attempt to distribute power thoughtfully, but constitutions are interpreted by the people living under them. And after 100 years, those people will have experiences and imperatives that the founders could not have anticipated. The generation ship, from a political theory standpoint, is a laboratory for questions about self-governance in the absence of external accountability. Its population must maintain functioning institutions without recourse to outside courts, outside enforcement, outside legitimacy beyond what they construct themselves. Whether human beings are capable of that across the span of centuries is a genuine open question, the destination problem. Now consider what happens if the ship arrives. After 2 centuries of travel, sustained across 10 generations of people who devoted their entire lives to a mission defined before any of them were born. After all that, the ship approaches Proxima Centauri. The star grows in the observation windows, slowly becoming something you can see is a disk rather than a point. The sensors begin returning data on Proxima b. The moment that has been the entire purpose of the civilization inside the hull is finally, actually happening. And then the data comes back, and Proxima b is a lifeless rock. No atmosphere, no water, no possibility of surface habitation. Stripped clean by billions of years of stellar flares. This is not an implausible scenario. As we discuss in Part 1, we genuinely do not know whether Proxima b is habitable. The observational data we have is consistent with multiple possible states, ranging from a world with liquid water and a significant atmosphere to a desiccated, airless body. We will not know which it is until we can observe it at close range. What does the civilization aboard the ship do? They cannot go back. The journey has already taken the entire lifetime of the civilization. There's no home to return to in any meaningful sense, only a distant planet for which they are more removed, culturally and temporally, than any group of humans has ever been from any ancestral home. They can remain in orbit around Proxima Centauri, but the ship was not designed for permanent occupation. It was designed to get people to a world, not to be a world indefinitely. And there may be no second destination within reach. This is what some researchers call the destination problem, and it is among the most underexamined risks in the serious literature on interstellar colonization. Every generation ship design assumes a viable destination. None of them, as far as the publicly available record shows, contains a fully developed contingency plan for arrival at an uninhabitable world. A related problem is what the computer scientist and futurist Andrew Kennedy described in a 2006 paper in the Journal of the British Interplanetary Society as the weight calculation. Kennedy's argument is conceptual but important. Assume that the technology for interstellar travel improves over time. A ship launched today at 1% of the speed of light will take 420 years to reach Proxima Centauri. But if propulsion technology continues to improve during those 420 years, a ship launched a century from now might travel at 10% of the speed of light and could arrive before or around the same time as a slower ship, having launched 100 years later. The generation ship's passengers would arrive to find that faster. Later ships beat them there. Kennedy's paper attempted to calculate the optimal launch window, the point at which the probability of a faster ship being launched later and arriving first is low enough that launching now makes sense. His conclusion was that, given certain assumptions about the rate of technological improvement, launching a slow ship too early might indeed result in its passengers arriving to find human civilization already established at the destination. He estimated that the optimal launch time, under his assumptions, was a matter of centuries away. But the assumptions are inherently speculative, and the calculation has been contested. The weight calculation does not, by itself, argue against generation ships. It argues for humility about timing. But it raises a genuine philosophical question. Is it ethical to send people on a 400-year voyage when there is a possibility, not a certainty, but possibility, that their descendants will arrive to find that the people they left behind made a faster ship and got there first? The answer to that question depends partly on how you value the lives lived during the journey. If the journey is worthwhile in itself, if the people aboard live good lives, contribute to knowledge, raise families, created culture, then the arrival of a faster ship at the destination is not a tragedy. It is a coincidence. The mission was not wasted. But if the only value of the voyage is the destination, if the lives of the passengers are meaningful only instrumentally, as a means to an end, then a ship that arrives second to its own civilization has failed in a fundamental sense. This is yet another reason why the quality of life aboard the ship is not a luxury consideration. It is the philosophical foundation of the entire enterprise. The lifeboat argument. Set aside for a moment the question of Proxima B specifically, and ask a larger question. Why does any of this matter? The most serious argument for building a generation ship is not romantic. It is not the poetry of exploration or the wonder of new worlds or the ancient human pull toward the horizon. It is simpler and more brutal than that. Earth is one world. One world can be destroyed. Anything that depends entirely on one world for its survival is, on a long enough timescale, inevitably lost. Philosophers of existential risk, the study of threats capable of ending or permanently curtailing human civilization, have argued for decades that the long-term survival of humanity depends on becoming what they call multiplanetary, or eventually multistellar. Nick Bostrom of the Future of Humanity Institute at Oxford has articulated this position extensively. Toby Ord, in his 2020 book The Precipice, estimated the probability of human extinction or civilizational collapse within the next 100 years at roughly 1 in 6. Whatever one thinks of that specific estimate, and it is genuinely contested, the broader argument is difficult to dismiss. A civilization confined to a single planet faces a finite range of catastrophic risks, from asteroid impacts to supervolcanic eruptions to anthropogenic climate change to engineered biological threats, any one of which could end the project entirely. A generation ship, or more precisely, a successful interstellar colony, is the most complete answer to that argument that physics currently permits. An established human presence in another star system is, by definition, protected from any catastrophe that destroys Earth. A supernova would need to target both stars simultaneously. An engineered pathogen would face the barrier of 4 light years of void. A civilization that exists in 2 star systems is not immortal, but it is incomparably harder to extinguish than one confined to a single world. This argument has been called the lifeboat argument. The generation ship as an ark, preserving human civilization against the possibility of Earth's destruction or deterioration. It is a compelling argument, and it carries genuine moral weight. If you believe that human civilization has value worth preserving across deep time, and most people, on reflection, do, then the generation ship is not merely an adventure. It is an insurance policy. A deeply difficult, enormously expensive, morally complicated insurance policy. But an insurance policy. There are counter-arguments. Some philosophers argue that the resources required to build and launch a generation ship, resources that could alternatively be directed toward reducing existential risks on Earth, toward climate mitigation, disease prevention, poverty reduction, or conflict resolution, represent a misallocation of moral priority. The lifeboat argument on this view is a distraction from the more urgent and tractable work of ensuring that the one world we have remains habitable. This is a genuine tension, not a false dilemma. It is not obvious that building a generation ship and addressing terrestrial risks are mutually exclusive. A civilization capable of one might be capable of both. But it is also not obvious that they are complementary. The resources are real and the trade-offs are real. What most ethicists who have engaged with this question seem to agree on is that the lifeboat argument is strongest not as a justification for generation ship as an immediate priority, but as a justification for taking the question seriously, for doing the science, for building the knowledge base, for maintaining the conversation. So that if and when humanity reaches a point where building such a ship becomes feasible, technically, economically, socially, the ethical and philosophical groundwork has been laid, and a decision can be made thoughtfully rather than in haste. The silence between the stars. And now we come to the last question, the one that cannot be answered with a number or a policy or a design specification. What is home? Consider a person, a child, let us say, born aboard the generation ship at roughly the midpoint of the voyage. She is the 6th or 7th generation of her family to be born within those walls. Earth is an abstraction to her. She has seen photographs of oceans, of forests, of open skies stretching to horizons she cannot conceive of. She has heard recordings of rain. She knows, as a fact, that there is a planet her ancestors left behind, and that it is still there, or was the last time light from it reached the ship, and that people still live on it, though those people are now separated from her by so much time and distance that correspondence is impossible. Her home is a ship, not in the way that a soldier far from family might say, wearily, that the barracks have become home, not in the way an expatriate might say that a new country has started to feel like home after years of adjustment. Her home is the ship the way your home is the world. The particular smell of the recycled air is, to her, the smell of all air. The hum of the rotation system is the sound of silence. The artificial lighting cycle is the rhythm of days. She has never seen a real sky. When researchers at the Institute for Advanced Study and at various universities have written about the psychological dimensions of long-duration isolated living, the concept that emerges most consistently is place attachment. The emotional bond that forms between human beings and the physical environments they inhabit. Place attachment is not merely nostalgia or sentiment. It is a cognitive and emotional orientation that shapes how people understand identity, belonging, community, and meaning. People attach to places that are familiar, that hold their memories, that contain the traces of significant events in their lives. The place does not need to be beautiful or comfortable to be deeply attached to. It needs to be known. For the people born in the middle of the generation ship voyage, the ship is not a compromise. It is not an inferior substitute for a real world. It is the world. Their place attachment will be to its corridors, its parks, its agricultural bays, its communal gathering spaces. The destination, Proxima B, will be for them the alien thing, the unfamiliar, the unknown. This matters enormously for the mission's final phase. The assumption embedded in most engineering discussions of generation ships is that the passengers will want to land. That arrival will be an unambiguous triumph, that the generations who have waited for this moment will rejoice and begin immediately the work of establishing a surface settlement. But if the people who arrive have no living connection to a surface world, if their home is the ship, not the planet, then arrival may be more psychologically complex than that. The planet is the destination their culture has told them about. It is the reason for everything. But it is not home. Home is the ship. Philosopher and cognitive scientist Arlie Bellows, writing in the context of space ethics in the mid-2020s, has described this as the arrival paradox. The people most capable of beginning the colonization of a new world, those who have grown up in the enclosed environment, who know every system of the ship, who have never been paralyzed by the vast open spaces of a planetary surface, may also be the people most psychologically challenged by the transition to living on one. The skills that made them good at living in the ship may not translate directly into the skills needed to live on a world. There is no clean resolution to this. It is one of the questions that can only be answered by the people who face it in the moment they face it. They will bring their own resilience, their own adaptations, their own understandings of what the mission means and what the destination demands of them. We cannot decide for them how they will relate to the sky when they first see it. Assuming the sky is there, what we can say is this: the meaning of home is not fixed. It is made. Every human community that has ever migrated, whether across a mountain range, an ocean, or eventually between planets, has made a new home out of a new place, carrying some portion of the old meaning with them and building new meaning from the materials of a new environment. The generation ship will be, among many other things, an unprecedented experiment in how far that making can go, how much a home can be carried in memory and story and practice across the void into the silence between the stars. The people who arrive at Proxima Centauri, if they arrive, if the destination is viable, if the ship survives, if the civilization within it holds together across centuries, will not be the people who left Earth. They will be people formed by a world their ancestors built and their grandparents' grandparents tended and their parents gave their lives within. They will carry Earth in the way any diaspora carries an origin, imperfectly, selectively, with transformations they cannot fully see, and they will stand for the first time under a red dwarf sun that is both alien and theirs, on a world that their ancestors' decisions made possible. And in that moment, in whatever moment of recognition or wonder or grief or something that has no name yet, they will discover what home means for a species that left its cradle and crossed the dark. We cannot know what they will find in themselves, but we can say with some certainty that it will be human, whatever that word means to them by then.